Hello everybody and welcome to the fourth and what is actually the final lesson in our circular motion topic. Just to quickly recap last lesson, we looked at finding the physical force in any circular motion example and equating it to the centripetal force. The example that we used was Coulomb's law in a hydrogen atom, and we simply said that by taking Coulomb's law, Q1, Q2 over 4 pi epsilon naught r squared, that if in the case of a hydrogen atom it is keeping that electron moving in a circle, we can equate that to one of our centripetal force equations, either mv squared over r or m omega squared r. Now for that particular example and the other examples that we looked at last lesson, there was only really one force that was acting in any particular example. What we're going to look at today is where there is more than one force acting and how we deal with that. Now, to give you an idea of where we might get more than one force acting, on the screen in front of you, you can see a picture of the London Eye. Now, we know that the London Eye is basically just a big Ferris wheel that rotates around. Let's imagine that we are in this capsule here, pretty much at the top of the London Eye. If we think about the capsule itself, there are a couple of different forces that are acting at any one time. There is the weight of the capsule, which is going to act straight down, and obviously weight is mass multiplied by acceleration due to gravity. And there will also be a tension force which will be acting towards the centre of the circle in order to keep everything in place. Now, I know it's obviously quite complicated on a structure like the London Eye, where you've got all the different cables, etc, etc, but the tension overall will still act towards the centre of that circle. So in order to study exactly what's going on here, we'll introduce the term vertical rotation. So any object that's been rotated vertically, such as a Ferris wheel, such as the London Eye, such as a car going over a bridge, or simply whizzing a stone around on the end of a piece of string. Now the good news is that for the purposes of our course, we only need to look at two different situations. We need to have a look at when the object is at the top of the circle, and we need to look at when the object is at the bottom of the circle. The approach that we're going to take is exactly the same as the approach we took last time. We're going to find an equation for the force that's acting on our object, and then we're going to equate it to centripetal force. Here though, because there isn't just one force acting, because we're dealing with more than one force acting, what we need to find is the resultant force that's acting on the object first. Let's have a look at the one at the top first and draw a line to the centre of the circle. Now we've said that we already know that there are two forces acting. We have the weight, which will always be acting straight down, mg, and we also have the tension, which will be acting in the string or whatever it is that's keeping it moving in a circle. Because those two forces are acting in the same direction, the resultant force, and we know that that resultant force is acting down, that resultant force will be the tension plus the weight, and we add them together because they are acting in the same direction. When the object is at the bottom of the circle, we've once again got the weight, which is acting straight down. This time though, the tension in the string is acting back up towards the centre. Our resultant force, because they're acting in opposite directions, we now have to subtract the weight from the tension. Now I've done it that way round because I know that at this point our resultant force has to be acting up, because it still has to be acting towards the centre of the circle in order to keep our rules about centripetal force working properly. So once we've done that and we've worked out what our resultant force is, we can, as we did last lesson, equate those to either of our centripetal force equations. Now before we move on to the next slide, I just want to have a deeper look at tension. And I'm just going to take both of these equations, I'm going to rearrange them to make tension the subject of the equation. In our top equation, if we subtract weight from both sides, we see that tension is equal to centripetal force minus the weight. And when we're at the bottom, we need to add the weight to both sides of the equation. So our tension becomes our centripetal force plus our weight. If we remember back though, the one thing that we know about centripetal force is that because we're treating omega as a constant, when we consider centripetal force as m omega squared r, because omega is a constant, in the situation that we're looking at, mass is a constant, and obviously being a circle, r has to be a constant. We can take centripetal force also to be a constant. When we consider that back over with our tension, if centripetal force is a constant in both of our equations, the weight will also be a constant, and therefore this sign, the negative sign here and the positive sign here, tell us quite a lot about the tension. In the top equation, because we're subtracting the weight from the centripetal force, that means that at the top of our circle, the tension will be at its minimum value. At the bottom of the circle, because we're adding the weight in, we've got that plus sign there, the tension will be at its maximum. So we can see from that that the tension will always be its minimum at the top of the circle and will always be its maximum at the bottom of the circle. What we need to consider then, given that the tension at the top of the circle is a minimum, we need to consider what the limiting factors on our motion are. Now what we're looking at is how fast does that object have to be rotating in a vertical circle in order to keep it rotating in circular motion. Imagine this, imagine that we are rotating something on the end of a piece of string in a clockwise direction. If we don't have enough velocity, if it's not moving quick enough to get to the top of the circle, it will get to a point in our circle and all the tension will disappear, and it will then end up moving in a parabola, probably more like a projectile at that point, rather than staying in circular motion itself. Let's now have a look at exactly how fast we need to be moving in order to keep it rotating in a circle. So let's now draw back in our radius. Here's our object, and let's draw back in our forces. We've got the weight and we've got the tension. And we saw from the last slide that at the top, the tension is equal to the centripetal force minus the weight. Now, when we think about limiting factors, in order to keep our object moving in a circle, this tension here has to have some minimum value, and that minimum value is 0. As long as the tension doesn't fall to zero, or doesn't, I know we can't get below zero, but mathematically doesn't get below zero. As long as we keep some tension in that string, the object will continue to rotate in a vertical circle. Now what I suggest you do is maybe go and try that, go outside in your garden, get an object on a rope or something like that, and have a go at rotating it in a vertical circle. As you slow down, you'll notice that that object doesn't actually get to the top of the circle. It will probably fall off from the circle, stop its circular motion, but the faster that you rotate it, it will stick in that circle. So our tension has to have a minimum of 0. What we can do now is we can use that information to work out what our minimum velocity and our minimum angular velocity are. If we take 0 as our limiting factor, so we take 0 as the absolute minimum that tension can be, we can see that 0 is equal to centripetal force minus the weight. We can now rearrange that by adding the weight back into each side to say that the centripetal force must equal the weight for our minimum values. We obviously have two different ways of looking at centripetal force. We have mv squared over r equals weight, and we have omega squared r equals weight. Now what we can see in both of these equations is that on each side we have the mass. So we can go ahead and cancel that out. Cancel, 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 cancel. Now interestingly, from a mass point of view, you would probably just cross out those m's and move on. From the physics point of view, whenever we do that kind of cancellation, we always think about what the implications of that are. What we're saying here is that when it comes to minimum velocity or minimum angular velocity, the mass that's on the end of that string makes absolutely no difference whatsoever. It is irrelevant. So thinking about that from a mass on the end of a string point of view, it makes absolutely no difference whether it's a pebble or a big stone on how fast we've got to rotate it in order to keep it moving in a circle. What we can do now then is just rearrange our equations. V squared is equal to G times R. Square rooting through, we can see that our minimum velocity is equal to the square root of G times R. On the omega side, we're going to divide both sides by R, so omega squared is G over R. And square rooting, we get our minimum angular velocity as the square root of G over R. So now let's have a look at an example. A stone of mass 150 grams is rotated in a vertical circle on a string of length 1.2 meters. Calculate the minimum angular velocity required to keep the stone rotating and the maximum tension in the string at that angular velocity. So in other words, taking the angular velocity that you've calculated in A and working out what the maximum tension in the string will be. As usual, pause the video, have a go yourself, and come back and carry on the video as soon as you think you've got an answer. So let's have a look at the answers then. Firstly, for A, for our minimum angular velocity, we saw from the last slide the minimum angular velocity is the square root of G over R. So that's going to be the square root of 9.81 divided by our radius, which is 1.2 meters. Once you've plugged that into the calculator, what you should find once we've rounded is 2.86, and of course the unit here being angular velocity is radians per second. For part B then, The maximum tension in the string acts at the bottom of the circle. So from a couple of slides ago, we have the equation T is equal to the centripetal force plus the weight. Now, because we've already calculated omega, it makes sense to take omega squared r and add the weight into that. Plugging the numbers into the equation then, the mass is 0.15, let's put this in brackets, times 2.86 squared times 1.2 plus our weight, which is 0.15 multiplied by 9.81. Once again, plug that into your calculator and you should get your final answer as 2.94 newtons. In summary then, our approach to problems where we have more than one force is exactly the same as when we only had one force. Here though, the first thing we have to do is to find the resultant force acting on any object rotating in circular motion. Once we've calculated that, we can then equate it to centripetal force in order to calculate everything that we need about that motion in a circle. We also looked at the minimum values. The minimum value for velocity in order to stay in circular motion, if we're moving in a vertical circle, is the square root of gr, and for omega the minimum value is the square root of g over r. So that's it for this lesson, and in fact that's it for this circular motion topic. So I hope you enjoyed that. I hope you've got a lot out of it, and of course look out for more topics coming soon.